Hi everybody, and welcome to our module on free radicals. In the video on cell injury, I talked about 4 mechanisms by which a cell can be injured, and the last one, which is free radicals, is a big topic, so that's what we're going to talk about in this video now. Let's start by going through some vocabulary. A free radical is a molecule that has a single unpaired electron in the outer orbit. Free radicals are highly reactive. They often donate electrons to other substances, and in terms of cellular biology, they can damage many cellular components, including the cell membrane, proteins, and other structures. Reactive oxygen species are free radicals that contain oxygen, and as you know, our bodies use oxygen for energy, and therefore reactive oxygen species are the type of free radicals that are often involved in cell biology. Reactive oxygen species come in several forms. One is called superoxide, the other is hydrogen peroxide, and the final one is the hydroxyl radical, and all of these can be produced inside of cells and potentially cause cellular damage. Normal healthy cells in our body generate free radicals even under normal conditions. However, those free radicals are inactivated, and the result is that the cell maintains a relatively low level of free radicals under normal conditions. There's some generation, there's some inactivation, and at any point in time only a small amount of free radicals is present inside the cell. There are many pathologic processes, however, that lead to high levels of free radicals inside of cells, and this can lead to cell injury and death. And this is why free radicals are such a basic principle of pathology, because they underlie many different disease processes. Let's talk about some of the ways that free radicals are generated inside our cells under normal conditions. Normal cellular metabolism using oxygen generates small amounts of free radicals. This occurs because oxidative phosphorylation yields small amounts of superoxide. It is quickly converted to hydrogen peroxide, another free radical, by an enzyme called superoxide dismutase. And hydrogen peroxide is more stable and it can cross membranes, and it's ultimately converted to water. So in this method, the normal superoxide ions that are made as part of oxidative phosphorylation are inactivated and converted into water. And this happens as part of normal oxidative phosphorylation, so there's always some of these free radicals inside of cells as this process is ongoing. Free radicals are also generated by radiation, so we're all exposed to radiation to some degree when we are out in the sun. UV light contains some radiation. In addition, if you have an X-ray or a CAT scan, that is also a source of radiation. And the fact that radiation can generate free radicals in damaged cells is useful in treating cancer. The goal of radiation therapy, which is what this woman is receiving in this picture, is to bombard the tumor with radiation and generate free radicals and basically kill tumor cells by free radical poisoning. Now, in addition to radiation, a couple of other mechanisms by which free radicals are generated inside of cells include metabolism of drugs, transition metals, and something called the respiratory burst. And in the next few slides, we'll talk about these 3 things. The metabolism of drugs in our body is classically divided into 3 phases. In the first phase, drug molecules are modified. This often happens in the liver. In the second phase, drug molecules are conjugated to other molecules. In the third phase, there can be additional modifications to the drug molecule and ultimately excretion. The cytochrome P450 enzymes are an important set of enzymes for drug metabolism found in the liver. They're found in the smooth endoplasmic reticulum of hepatocytes in the liver, and they participate in phase 1 metabolism, drug modification. And for some drugs, what they do is generate free radicals that are called bioactive intermediates, and this can lead to cellular damage, especially liver damage. So for some drugs, modification through the P450 system generates drug-free radicals, and if these drugs are taken in excess amounts, this can lead to liver toxicity. In the videos on the liver in the GI section, I talk about the liver zones. The hepatocytes between the portal triads in the liver and the drainage from the liver to the hepatic vein are divided into 3 zones. The periportal zone is closest to the portal triads, and the central lobular zone is the furthest away from the portal triads. It is in zone 3, the central lobular zone, that you find P450 enzymes, and if you know that, then you should know that this is the zone where free radical damage is going to occur when medications are consumed that generate excess free radicals. And here's a biopsy slide of the liver showing the zones. It's right here, zone 3, that you are going to see the damage when patients take drugs that are metabolized by the P450 system into free radicals. The classic example of a drug that causes free radical damage to the liver is acetaminophen or Tylenol. Tylenol is metabolized into a substance known as NAPQI or N-acetyl-P-benzoquinone-imine. NAPQI is a reactive oxygen species and it causes free radical damage in the liver. This is shown at the bottom of the screen. This is the structure of acetaminophen over here. It's also called paracetamol. The P450 enzymes metabolize it into NAPQI, which is a free radical, and that can damage cells in the liver. And that's why Tylenol is toxic to the liver if you take too high of a dose. Transition metals are another source of free radicals inside cells in the body, even under normal conditions. Earlier, I talked about how oxidative phosphorylation generates superoxide, which is converted to hydrogen peroxide for inactivation by converting it to water. However, if there are transition metals around, instead of the hydrogen peroxide being inactivated, it can react with the metals. Hydrogen peroxide enters something with metals called the Fenton reaction. This is shown on the screen here for iron and copper, two metals found in our body. They can react with hydrogen peroxide and become oxidized and generate the hydroxyl radical. What this means is if you have lots of iron and copper around, then instead of all your hydrogen peroxide going into water, which is what should happen, it will react with the metals and form hydroxyl radicals, which can cause free radical damage. And this is the mechanism by which people suffer tissue damage when they have hemochromatosis or Wilson's. I talk about these disorders in the GI section, but they both involve excess amounts of either iron or copper. And the way they cause toxicity is that instead of the hydrogen peroxide getting inactivated, it reacts with the metals and forms more free radicals. And because of the possibility that transition metals can form free radicals which can damage cells, our body has evolved storage proteins and transport proteins to protect those free metals from entering the Fenton reaction. So iron is often found bound to either transferrin, ferritin, or lactoferrin. Copper is found bound to ceruloplasmin. And the reason we have these proteins is that binds the transition metal and keeps it from entering the Fenton reaction and generating free radicals. Another source of free radicals inside the body is the respiratory burst. This is something that phagocytes do when they have engulfed bacteria inside the phagosome in order to kill the bacteria. One of the ways that phagocytes can kill bacteria is by generating hydrogen peroxide inside the phagosome where the bacteria is found. So if you look on the screen here, what phagocytes do is they bind to the bacteria or whatever invader is in the body. They place it inside a small package inside the cell called a phagosome. And then what they do is they use a biochemical process called the respiratory burst to generate hydrogen peroxide in order to kill the bacteria. The generation of hydrogen peroxide by the respiratory burst requires three key enzymes. The first one is NADPH oxidase, the second one is superoxide dismutase, and the last one is myeloperoxidase. And here's how the respiratory burst works. Phagocytes begin with oxygen. The enzyme NADPH oxidase, an enzyme which requires NADPH, converts oxygen into superoxide. Then superoxide dismutase synthesizes hydrogen peroxide, and then myeloperoxidase uses chloride to create hypochlorous acid. And all of these substances here contribute to bacterial death inside of phagocytes. So now we've talked about ways that free radicals are generated inside our body, things like oxidative phosphorylation, radiation, etc. Now let's talk about some of the ways that our body inactivates free radicals so that it can maintain a low level under normal conditions. Well, first of all, free radicals spontaneously decay, so to some degree they just go away on their own. In addition, antioxidants are substances inside of cells that are free radical scavengers, and these bind free radicals and eliminate them, and this protects the cell from free radical damage. So vitamin E, vitamin A, and vitamin C are all antioxidants, and so is the substance glutathione. There are also enzymes in our body that can inactivate free radicals. Catalase is found in the peroxisomes in our body. Superoxide dismutase is found in the mitochondria, and we talked earlier about how this can eliminate free radicals generated by oxidative phosphorylation, which occurs in the mitochondria. Glutathione peroxidase is another enzyme in cells. It's found in the cytoplasm. It gets its name because it requires glutathione, and it uses glutathione to inactivate hydrogen peroxide and turn it into water. And I've shown this at the bottom of the screen. So oxygen can be converted into all of these free radicals, and catalase, peroxidase, and superoxide dismutase all in one way or another help to convert those free radicals into water. There are two super high yield disorders that the boards love to test you on. They're both very rare, but they have tie-ins to everything we've been talking about up to this point regarding free radicals. The first one is CGD, or chronic granulomatous disease. People with this disorder have an immune deficiency syndrome and are vulnerable to infections. The underlying problem is that they lack normal functioning of NADPH oxidase, that enzyme we talked about being part of the respiratory burst. This means that for these patients, their phagocytes cannot generate hydrogen peroxide, and therefore they cannot effectively kill bacteria. If we go back to this slide, patients who are defective in this enzyme can't generate any of these free radicals to cause bacterial death. It turns out, however, that they are not vulnerable to infections by every organism. Some organisms they can fight off. Bacteria can be either catalase positive or catalase negative. The catalase enzyme, if bacteria have it, in other words, if they're catalase positive, allows the bacteria to break down hydrogen peroxide. If we go back to this slide, this is what catalase does in our own body. It converts hydrogen peroxide into water. Well, some bacteria are catalase positive, and they also have the ability to convert hydrogen peroxide into water. In those catalase positive bacteria, there is not going to be any hydrogen peroxide around, even inside the bacteria. So patients with CJD cannot generate their own hydrogen peroxide and free radicals, and they also cannot find any inside the cell if they are infected with catalase positive bacteria, and this leads to recurrent infections. Bacteria that are catalase negative, however, will generate their own hydrogen peroxide. This can be generated as part of normal bacterial metabolism, and when this happens, the phagocytes can use the H2O2 from the bacteria and create free radicals. If we go back to this slide, bacteria that lack the catalase enzyme will synthesize some hydrogen peroxide as part of normal metabolism. Myeloperoxidase can use that hydrogen peroxide to make hypochlorous acid, and together the phagocyte can use these two substances to cause bacterial death. Thus, they are more able to kill catalase negative bacteria compared to catalase positive bacteria that do not generate hydrogen peroxide. And so because of all this biology related to the catalase enzyme and free radicals and the respiratory burst, there are 5 organisms that cause most of the infections in patients with CJD. They're shown on this slide here, and all of these are catalase positive. They break down their hydrogen peroxide and don't leave any for the phagocyte to use. The second super high yield disorder when it comes to free radicals is G6PD deficiency. In the biochemistry video on the HMP shunt, I talk about this disorder in detail. It's an enzyme deficiency disorder where patients can't synthesize normal quantities of NADPH. But for our purposes here, I want to focus on the free radical aspects of this disorder. Patients with G6PD deficiency have a limited supply of glutathione, and this makes them vulnerable to red blood cell damage by free radicals, which leads to recurrent episodes of hemolysis. That's the hallmark of this disorder, is recurrent hemolysis. And one of the classic triggers for hemolysis in patients with this disorder is fava beans. G6PD deficiency occurs in some parts of the world where people eat lots of fava beans, and if they have this condition and they eat fava beans, they will develop hemolysis. The reason this happens is because fava beans contain a compound known as vicine. This is its structure on the bottom left side of the screen. It's metabolized in our body to divicine, which can generate reactive oxygen species. So first of all, when you eat fava beans, you generate more reactive oxygen species and more free radicals. In addition, our cells try to inactivate the reactive oxygen species by using glutathione, but these patients have a limited supply, and therefore they run out of glutathione and they suffer from hemolysis. If we go back to this slide, one of the mechanisms for free radical inactivation is the enzyme glutathione peroxidase. It's found in the cytoplasm of cells, including in red cells. It requires glutathione to function, and it uses glutathione to convert hydrogen peroxide into water. So in a person with G6PD deficiency, there's a limited supply of glutathione, and this leads to an inability to inactivate free radicals, and that leads to free radical damage and hemolysis. So now that we've talked about how free radicals are generated and how they're inactivated, let's talk about exactly how they are toxic to cells. I told you before that cells don't like free radicals, but now let's talk about why that's the case. Basically, free radicals do 3 major things that are bad for cells. The first thing is they peroxidize lipids, and it's very high yield to know this. A peroxide is a substance with 2 oxygens bound together, and if you look at the right side of the screen, you can see how lipids can get peroxidized by free radicals. So any lipid that is unsaturated, meaning it has at least 1 double bond, can react with free radicals and become a lipid radical. That lipid radical can then react with oxygen, and ultimately what you end up with is a lipid peroxide. These are not good for cells. When they occur in lipids of the cell membrane, they damage the membranes, and this is one of the ways by which free radicals can damage cells. In addition, free radicals can oxidize proteins, and this damages important enzymes inside the cell, and they can also disrupt DNA. They can cause breaks in DNA and cross-linking, and all of these things are how high levels of free radicals are damaging to our cells. So now I'll finish this video with a couple of clinical examples of free radical induced injury. And the first one we'll talk about is called reperfusion injury. So when patients have a myocardial infarction, which I talk about in detail in the cardiology section, there's decreased blood flow to the myocardium. This is an example of ischemia. When that myocardial infarction is treated and the thrombus in the artery resolves or is treated with angioplasty, blood flow is restored. This is called reperfusion, and blood flow returns to the myocardium. When you do this, this is overall a good thing for patients. Some reversibly injured cells recover and there's less myocardial damage overall. However, people have studied this in detail in the basic science laboratory, and it turns out that some cells are actually damaged by reperfusion. This is bad, and it's paradoxical because we think that restoring blood flow is good, so it's a surprise that it turns out it's bad in some cases. There are several mechanisms behind this, but one of them is the fact that when you restore the oxygen supply to the myocardium, you generate free radicals, especially in areas of the myocardium that have been damaged. Those areas have lost antioxidants, and they're less able to tolerate the free radicals that come with the resupply of oxygen. In addition, mitochondria have been damaged, and they can only incompletely reduce oxygen, so they generate more free radicals than usual. So for both of these reasons, reperfusion damages myocardium to some degree, even though overall it is a beneficial thing for patients. Another example of free radical damage is carbon tetrachloride. This is an industrial solvent that used to be used in the dry cleaning industry, but it's now banned because the liver is highly sensitive to damage in people exposed to this over time. The reason damage to the liver occurs is because carbon tetrachloride is converted to CCl3, which is a free radical, by P450 enzymes in the liver, just like we talked about earlier. This leads to lipid peroxidation, as we talked about earlier, as a consequence of free radical damage. In addition, in the liver, what happens is lipoproteins are no longer synthesized and secreted normally, so there's an accumulation of lipids. So the classic finding in a patient years ago who had carbon tetrachloride poisoning was that their liver would be filled up with fat. Eventually, the buildup with fat and other consequences of free radicals would lead to cell death and liver failure. And I'll finish this video with lipofuscin. This is an insoluble cellular pigment. It has a yellow-brown color that I'll show you in a minute, and it's commonly seen on examination of biopsy specimens. Lipofuscin contains oxidized lipids. It's made up of oxidized lipids, and these are thought to be derived from lipid peroxidation from free radicals like we talked about earlier. As we get older, over time, lipofuscin accumulates in our lysosomes, and that's why you can see it on biopsy specimens. The good news is it's generally not pathological, meaning it does not cause disease. However, it is seen as people age. So when you examine biopsy slides of older patients, you will commonly see lipofuscin. It does not mean there's any disease process going on, it's just a sign of aging. And here's a biopsy slide of muscle tissue and the arrows pointing to the yellow-brown lipofuscin pigment, a common finding when you examine tissue in biopsies of older patients. And that concludes our video on free radicals.